Hello there. So this is section 6.3, video number 1. So remember in section 6.2, we introduced this idea of an orthogonal projection of one vector onto another, or maybe even more generally, one vector onto the line defined by another single vector. And so I may not have pointed it out specifically in that video, but if you look at the line defined by a single vector in the two-dimensional plane, or really for that matter in any dimension, that line is actually just the set of all vectors spanned by that one vector u. And so what that means is that, in fact, basically this is a subspace of dimension 1 with basis u. And so I say that because what we want to do in this section is kind of generalize that idea in order to calculate the minimum distance from some vector y to an entire subspace W. And what we're going to do here is maybe allow this subspace W to be generated by, or to have dimension greater than 1. That is, what if W has a basis of 2 or 3 or 4 vectors? So on the board behind me, I have a diagram in R3 of sort of what I mean. So suppose here, just for example, that U1 was the vector 1, 0, 0, depicted here, and U2 was the vector 0, 1, 0, which is on this axis, right? So each of these vectors fall on one of the axes in R3. And so this shaded area roughly represents the subspace generated by U1 and U2. So if you can imagine, like in R3, the span of two vectors defines a plane, right? So if you can imagine sort of taking a flat two-dimensional plane, that's what the subspace spanned by these two vectors is generating, right? These two vectors are never going to be able to have any sort of positive or negative or any non-zero value on this axis here, but they can manage to cover every single vector on this plane. So what if we now wanted to find the minimum distance from, say, some vector y, which didn't lie on this plane? Well, we'd want to find some vector y hat that did fall on this plane. And again, we'd want to minimize the distance of this line here connecting y and y hat. And if I've drawn it right, you might once again see that this vector here should actually form a right angle with this plane. So what we're eventually going to see is that this vector y hat, which is the closest vector in this subspace W to y, and the resulting vector y minus y hat should still be orthogonal to W. So we're basically just going to generalize this idea and generalize the way we kind of talked about and kind of worked out this idea to now of, projection of one vector onto another, to the projection of one vector onto an entire subspace. So with that, I can state the main theorem of this video, the orthogonal decomposition theorem. And so this is theorem 8 in your book. For the sake of space, I'll just state it. This is the orthogonal decomposition theorem. And so it says that also in the notes. So let W be a subspace of Rn, and each vector y in Rn can be uniquely written in the form y is equal to y hat plus z where y hat is in the subspace W and z is in W perp. And remember, this means that z is orthogonal to w, right? Meaning that the dot product of z and any vector in w is 0. But not only that, so we know that we have this unique representation of y as vector in w plus vector orthogonal to w. We actually also know how to calculate y hat. And so we actually know that if we have an orthogonal basis, and so notice here I've actually also drawn u1 and u2 to be an orthogonal basis, but in general, if we have an orthogonal basis of p vectors, for w, then we actually know what y hat is, and it should look a lot like the orthogonal projection of y onto a single vector, because it is in fact the sum of the orthogonal projections of y onto the basis vectors. Apologize, this does take a little bit of time to write the whole thing out. So y is in fact just the sum of the projection of y onto u1 plus y onto u2 plus y onto up. And so each of these terms is y dot u1 over u1 dot u1. And remember again, this fraction is actually just a scalar, times the vector u1 plus, now same thing with u2 and so on. And then on top of that, once we've calculated y hat, z becomes straightforward to calculate because it's just y minus y hat. And so then notice, I'll write it here in a second, and actually, well, I'm not going to write it down because we're going to prove it next video, but this vector z, its length is the minimum distance from y to the subspace w. And like I said, we'll actually prove that as a theorem in the next video. So, a few notes about this, and then we'll quickly talk about the proof. So like I said, just to state it, this is called the orthogonal decomposition theorem. And the vector y hat in theorem 8, or in the orthogonal decomposition theorem, is called the orthogonal projection of y onto w. And it's denoted kind of in the same way, projection of y onto w. And so this is maybe the more common way of writing y hat. So how can we prove this theorem? So what I want to do is, given that we already have this definition of what y hat should be, and I'll leave this up on the board, we're going to quickly show first that z is orthogonal to w. After doing that, well, we have this decomposition of y into y hat, which, as you can see, definitely is contained in w, right? Because y hat itself is just a linear combination of the basis vectors u1 through up. Remember that each of these fractions is a scalar, so y hat is contained in w. Z is orthogonal to w, we'll show that. after that, we just want to show that this decomposition is in fact unique. That is, if there was another decomposition that obeyed these properties, in fact, it had to have been this decomposition the whole time. And I'll explain what that means here in a second. So I'm going to leave up y hat as we prove this theorem, and we'll leave up what z is. There we go. All right, proof of theorem 8. And then actually we're just going to go through an example and then we'll be done for this video. But this proof is a little involved, I guess. So in this proof, again, like so many of the proofs before this, I've outlined kind of a way to do it. I realize that you can't really see anything on that. I've outlined a way to do it, so I'd highly recommend looking through those steps first and then watching the video. So the first step, I've actually kind of already mentioned it, but we're going to let u1 through up be an orthogonal basis. For W. And notice here, since y hat is actually just defined to be a linear combination of these basis vectors, we can just say by definition y hat is contained in W. So showing that y hat is in W is a fairly straightforward exercise. So next we want to show that z, which is equal to y minus y hat, is in W perp. Or maybe a better way of saying that, z is orthogonal to every vector in W. So remember I had introduced or talked about this idea that when we introduced orthogonal vectors, that if we wanted to show that one vector was orthogonal to an entire subspace, it suffices to show that that vector is orthogonal to an entire basis for that subspace. So what we're actually going to do to show this is we're going to show that z, and I guess there should be a vector sign over z, is orthogonal to the set, well, u1 through up. And notice, since this is assumed to be a basis for W, this is sufficient to show that z is in fact orthogonal to every vector in W. And so, much like a lot of the proofs here, we're actually just going to show that z is orthogonal to u1. And then after we do this step, I'll explain that basically you could do this step the exact same way for every single other basis vector, u1 or u2 through up. And so I'll leave it, well, you don't have to do it for all of the basis vectors, but because it'll end up being the same basic process that we're going to use to show that z is orthogonal to every other basis vector, we won't do it, and we'll just sort of talk about the fact that you can do it. So we want to show that z.u1 is equal to 0. So to do that, we should probably calculate z.u1, which, by the way we've defined z, is equal to y minus y hat dot u1. All right, so why does that help us? Well, we've defined y hat to be this following vector. So what I'm going to first do, well, actually maybe I'll distribute these two vectors through. So this is equal to y dot u1 minus y hat dot u1. Now I'm going to substitute in for y hat. But, well, I'll substitute and then I'll move on to the next step. So here I'm substituting what we've assumed y hat to be. Which is this linear combination of the projections of y onto the vectors in W. And then we're taking that and the dot product of U1. So I distributed through, substituted this in for y hat. Well, and now I'm going to distribute U1 through this sum. But remember, each of those fractions is just a scalar, so I don't care too much about it when taking the dot product. And remember that this is assumed to be an orthogonal basis. So when I distribute U1 through each of these terms, the dot product of U1 with every single vector U1 through UP is going, or sorry, U2 through UP is going to be 0, and I'm only left with the single term y dot U1 over U1 dot U1 times U1 dot U1. So to reiterate that last step, remember I'm going to distribute this U1 using the dot product through each one of these terms. Since each one of these fractions is a scalar, I can rearrange this as this scalar times the dot product of whatever vector I had, dot product with U1. But since this basis was assumed to be orthogonal, U1 dot product U2 is equal to 0, U1 dot product U3 is equal to 0, U1 dot product UP is equal to 0. So the only term that doesn't get zeroed out, so to say, is this one. But now notice I've got U1 dot U1 over U1 dot U1, and so this is equal to y dot U1 minus y dot U1, and almost by magic, this is equal to 0. And so basically you would do this for each other vector, just replacing this index with whatever index you wanted to show next. And in this step, it sort of would be key, you'd be left with only the term containing the same indexed vector, right? And so every time at this step, you'd wind up with y dot U2, U3, Ui minus the same y dot U2, U3, Ui. And so no matter which vector you'd selected, in this case we selected U1, you'd get 0. So as it turns out, Z is orthogonal to this basis, meaning Z is orthogonal to the entire subspace W. All right, so we have one more thing to show for the proof of Theorem 8, and then we can look at an example of this. So the theorem stated that this decomposition is unique. And what that means is that basically if I have, so I'll explain sort of what it means as we do the proof. So the way we prove this in math, to prove that something like this is unique, is we assume that there's actually another decomposition. And so I'll call this vector y sub 1 and this vector z sub 1. And the defining properties of this decomposition that we eventually want to show as unique were that y hat was contained in W and z was contained in W perp. So what I'm going to do is I'm going to assume that there's some other decomposition y sub 1 plus z sub 1, such that y sub 1 is contained in W and z sub 1 is contained in W perp. And my goal with this proof then is to show that in fact y sub 1 is equal to y and z sub 1 is equal to z. And if I can do that, I'll have shown in fact that there isn't another one, right? That any decomposition that looks like this has to be the original one we found, defined by y hat being this vector and z being this vector. So, since each of these expressions is equal to y, we actually know that y hat plus z is equal to y1 hat plus z1. Well, this implies, if I do some subtraction, that y hat minus y1 hat is equal to z1 minus z. So why does that help me? Well, notice that z1 minus z is in W perp. Right? Because both of these vectors are in W perp, and W perp is a subspace. But this means since these two vectors are equal, this vector, y minus y1, is in W and W perp. But by definition, if this vector is in W perp and W, the dot product of this vector and itself must equal 0. Because the definition of being in W perp means you're orthogonal to every vector in W. But if you're also in W, then you have to be orthogonal with yourself. But as we've already seen, this means that y hat minus y1 hat is equal to 0, which means that y hat is equal to y1 hat. And so then you could end up showing that z1 is equal to z because, well, since y hat is equal to y1 hat, this means that z1 minus z is also equal to 0, meaning that z1 is also equal to z. And so what we just did is we said, well, maybe there wasn't another decomposition. We used some known facts about what that decomposition would have to satisfy. Specifically, it would have to equal the other one. Using all of that, we showed, well, this decomposition which we had thought we'd found was in fact this original orthogonal decomposition. And so it turns out that if we want to express y as the sum of a vector y hat in a subspace W and a vector orthogonal to that subspace W, this is the only way to do it, by defining y hat like so, and then defining z accordingly. And this should make some sense. So given the length of this video already, I think I'm going to put off the example until the next video. But this should make some sense, right? Because our goal in defining this decomposition was to have y hat be the closest vector in W to y, right? We wanted to find the vector in our subspace that was as close to this vector as possible. And there shouldn't be, well, you might not expect there would be multiple of these vectors. Of course, maybe except in like a weird scenario, but you know, you'd expect this decomposition to be unique. I guess as I say, you wouldn't expect there to be multiple. I can think of maybe a few examples where there might be, but you know, for a lot of vectors, you'd expect that there would be sort of a closest vector in W to y. So anyways, so what we will do next, like I said, is go over an example. And then we will talk more about actually proving that, in fact, the length of z is, in fact, we can prove the closest distance from y to this subspace W. And then we'll do some theory problems.